Hey guys, right now it's 4:08 and I've noticed that my internet has been I'm pretty sure I'm back. Sorry about that. And it looks like it is recording. Cool. And I'm just waiting for one more thing to sort of spring into existence. And we'll see how this guy goes. Well, and okay, we'll just hope and pray. If you would be willing to pray to the God of your choice, I'd appreciate that my iPad is able to connect, because otherwise things will be a little bit different, probably not dramatically, but enough that it'd be noticeable. So yeah, I did a couple things that I'd like to draw your attention to, and where is that? Is it over here? Okay. Perfect. Okay. Go and nice. Okay, I found it finally. So what I'm going to be doing is sharing a screen, and once I've shared that screen, and I seem to have lost all of you. Okay, there you're back. Okay, share screen. And desktop, good, share. Okay, so I'm back in gear. And like I said previously, during our previous class session, I do really much better when I'm looking at you guys to the extent that you're capable of having your video on. I can tell who is like nodding along versus who's, maybe flipping me off or something. Whatever the case is, if I can see some of you, like as many as 2/3 would be great. I know that's not always possible, but what the hell? Help me out. So I got a few. Good. What I want to do is to sort of remind you of a couple things about organizational aspects of the class. And I think that's really the biggest challenge that most students face in the first week of a class, but also especially if it's double based and you guys have to be on top of stuff. Okay, so maybe let me make this a little bit bigger so you can see perhaps a little bit more easily. So I don't know the size of the screen you're looking at, but yeah, sort of within the class Canvas site. I'm just going to focus on right now on 1, 2, 3 things. One of them is, hey, you probably want to have JMP installed on your machine. Okay. If you haven't yet installed the software in the fashion that is suggested in this PDF document here, you can always just click on software.calpoly.edu, and then you'll probably see something like JMP16. Get it on your machine. If there's a problem, send me an email. I can always help out with that. Some students invariably say, well, I got it downloaded and I installed it, but then it asks for a license file. If that's the case, if it's in a situation where you're saying, well, I did this, that, and the other, tell me what you did and tell me what is not currently working, be as specific as possible, and I can most likely send you exactly what you need in short order. Okay, so get the software on your machine. Second is, although I try to put all of the data relevant for our labs in the lab file itself, some of you might want to just go ahead and click download all the data for the whole course. And I here have most everything that I know this term will be using. But if I do add additional files later, I will update this as we go. Okay, so if I add additional data out there for examples in class or for labs, I'll update this here. So if you want everything all in one spot, that's no problem. Now within week 1A, and that's where we're at right now, week 1A, and it basically is a quick overview of where we're at. And darn it, I need to upload the PDF of the PDF of the lecture slides I'll be using. I haven't done that yet, so I apologize for that. You can rewatch yesterday if you found that exciting. Watch it again; it's always fun. But today we're going to be going through new content, a t-test to compare two population means, and the t-based confidence interval to compare, again, two population means. The lab itself, if we click our way into it, it's going to be the sort of thing that you've seen before in some places. Darn it. Okay, so you're going to want to download, I think, the second of these two lab files, or it doesn't really matter, perhaps. But that's the one you're going to use for working with your group mates, because it's got all the questions in there. And the data set is also downloadable. So all the questions relate to the data set, and they match up to things that we've gone through or will be going through in class today. I sent you earlier a collection of information about other students' contact information. And I'm thinking you can look around the room, you can see the names of the folks here and infer from the names who's who, perhaps, in terms of the contact information. You might want to give a call or a text or set something up if you haven't already. Again, for labs for this class, you should be working in groups of ideally 4. 3 is fine. 2 is not as good as 3, but 5 is not allowed. Okay, so make sure that you sort of get into a lab group and you're all in good shape. I think that's it for what you're going to do after class. Fill out the lab problems, sort of download this, add your own content, and then upload your answers later in groups, and all should be good. Now, I think administratively, I've gone through and listed off a few things very quickly. The things I'm going to try and draw your attention to each of the first few days is the stuff that maybe matters the most. But there might be some questions from the point of view of administrative things that maybe I just mentioned and you want to clarify, or maybe I haven't mentioned, but you were wondering about. So I'd like to pause and see if you have any questions on administrative matters before we move forward. Okay, so
confirm we need Jump for this, right? Like we do need to download it for this.
For the lab activity, you should have GMP. For the class, you should have GMP. If you don't have it yet, that's probably fine. You just wouldn't be following along with me while I'm doing the work in class today, but you would want to download it, get installed before you sort of work away on the lab. And it's one of those things that you probably want just for exams alone. For exams, I write the exam such that a student could answer the exam completely correctly without using the data that I'll provide and the software GMP. Some students, last time I taught this, they did perfect or darn near perfect without using the software at all. Other students got used to using the tool in one way or another, and they used the software a lot for the purpose of helping out get stuff done or tackling problems, which I think a student could tackle conceptually, or maybe with the software, they can tweak a data set to help them answer a question. It's worked out quite well that students with a variety of approaches have been successful. So I'd say definitely worth getting GMP on your machine, unless you know that you are wanting to work with others and you're willing to let them do all of that and not have that around on a test.
Where do I get the license? Because mine's expired.
Okay, so just send me an email saying, hey, I need a current license, and I will just go ahead and download that myself, and I could reply. But if you go to the same place that you downloaded JMP in the first place, there should be the option of getting just the license file itself. If you don't see that, send me email. I'll email with a new revised license file. And if that's a problem, most of you could always just uninstall and reinstall from the new version. And that takes a little bit longer, but usually it works. So if I don't get back to you quickly enough with an email with the license file, that might be what some of you would do. Just wanted to mention, my kids sent me a little cute thing today, so I thought I'd share it with you, and that is this guy here. The poor T-Rex here simply can't raise the arm high enough that the instructor can spot that they have a question. Fortunately, you all have the little sort of under reactions, the ability to raise your hand, or you could just unmute, unlike this dude who doesn't seem to want to talk up in class. You could just unmute and let me know you got a question. So you did that perfectly, Cami. But yeah, I thought this was pretty cute, especially the I don't know, these are cute looking dinosaurs from my point of view, but what the hell is this pink thing? I was thinking Triceratops, but maybe Stegosaurus. It's hard to know. Okay, moving on. Any other questions on administrative things? Okay, so what I'd like to do then is to try one more time. If I could log in here and get access to this so that way I can, yes, looks like I'm in. Good. I just have to make myself a co-host so I can write on the screen if need be. Man, I'll make myself host, whatever. I'm all good. Yeah, you should be fine. Okay, so I'm in good shape as far as I can tell, and I've shared with you that screen, and we're good to go. Okay, so really what we're doing this beginning of class is what most of you would view as review material. Not all of you have done this recently, and so some of you might say, well, it's not exactly a review for me. That's fine. I want to start slow, and yeah, we're going to move fast perhaps in the first week or so, but because it's mostly review material for most of you, I feel okay about doing that. But I would love it if you stop me if you'd like me to elaborate on any of these issues a little bit more in depth, or if you think to yourself, I've got this question. Don't be that dinosaur, okay? Raise your hand, let me know. So the notes here, I've got them up there, but I want to sort of have in the background that so I can have some space to work on. And have I shared the screen yet? Share screen. Oh, darn it. I apparently did something really silly, and I'm no longer the host, which makes it a challenge. Okay, so I'm going to make myself the host. Okay. And now I have to make my other self a co-host. Good. Now I can share the screen. Lovely. And hopefully you can see this okay now. Do y'all see something at least? Yes, I win. Now, this box model is a way I like to view the material in the t-test. If we're essentially wanting to compare two population means, there's a couple different ways that we could go. One of the things that we might want to do when we're comparing two population means is to answer a question, is mu1, the mean of the first population, different from mu2, second population's mean? You know, two different groups, do they have different population means? I don't know. We could tackle that with a hypothesis test. Okay. How much larger is mu1 than mu2? That's another natural question, but that would be dealt with a confidence interval, CI for confidence interval. So our two different methods here have two natural questions. Darn it. Let's use a pen and no, not eraser, pen. You know, I'm really feeling flustered today. My router probably really screwed me up. Have you ever been like in one of those situations where like stuff goes wrong and then all of a sudden you get weird, like that flat tire on the way to the wedding, and then you show up at the wedding? By the time you get there, hopefully you're going to be okay, and hopefully as time goes by in class I'll get less flustered. Okay, so I've got these two natural questions. I've got these two different populations, mu, population 1, population 2, and conceptually I'm sort of thinking about this as though I've got well, shoot, these two populations in two separate boxes where I'm going to sample from each of them separately. Now, inside the first population, I've got a population distribution. Maybe it's not looking normal in shape, but there is a population mean mu1 from population 1. And I'm assessing population 1, population 2. And maybe I'm going to go with an example in a little bit, but let's just say weekdays and weekends could be the same on average, or maybe they're a little bit different on average. And I really want to know, is mu1, the weekday average, the same as or different than mu2, the weekend average? And I guess for the first population, we've got a standard deviation of sigma 1. For the second population, a standard deviation of sigma 2. Now, I don't know blue. Literally, stuff shown here in blue, those are characteristics of the whole population, the histogram, the shape of it, mu1, the mean of it, sigma 1, the standard deviation of that population. I do not know any of that information. However, I'm in a nice situation where I can take a sample of size N1 from population 1 and N2 separately from population 2. In each group, I could take a sample. From each group, I should say, I could take a sample, and I could summarize that sample information by y bar 1, or shoot for the second sample from the second population. I've got a second sample mean y bar 2. Similarly, S1, the standard deviation, and S2, the standard deviation. So I have information here, and I'm going to try and highlight it in red. Here we go. The green observable values, the green summary values, tell me information that will help me tackle either form of my question. So I'm going to save this here, do a quick screen grab and clear it. And if any of you ask me for the screen grabs upshot to upload this, I can. Please send an email requesting that if that's something that you would like. Okay, so I got my box model. I showed it to you a little bit, and the real thing here is I want to compare the two population means in some way. Now, I could, for a confidence interval, I could estimate mu1 minus mu2 with the difference of the sample means, and I'll show you an equation for that in a little bit. But the idea really is if mu1 is nicely estimated by y bar 1, and if mu2 is nicely estimated by y bar 2, I could estimate the difference of the population means, mu1 minus mu2, with y bar 1 minus y bar 2. So I'd be happy to estimate this unknown true value with sample data. And perhaps that margin of error, okay, plus or minus a certain amount, will give me information that helps me tackle my two separate questions. So a question comes to my mind, and that is, how far away is our friend y bar 1 minus y bar 2 from the actual truth, mu1 minus mu2? Again, you're estimating mu1 minus mu2 with the, which is unknown, with the difference of the sample means. Our standard error here tells us how close our estimate, y bar 1 minus y bar 2, is what we're trying to estimate. Let me say it a little bit differently, because I think I got my emphasis wrong. We're going to estimate mu1 minus mu2 with y bar 1 minus y bar 2. How close is our estimate to the number we're trying to estimate? Okay, it's about a standard error or so away. And you can spot here in our friendly equation for the standard error, it depends on things that are known, like the two sample sizes. And as you can spot here, the larger the sample size in each group, the smaller the standard error is. Similarly, if you know the standard deviations in each of the two separate samples, those are estimators for the unknown population spread. Essentially, if the data are clustered quite closely together in the sample, you think in the population, the data are clustered quite closely. And so a smaller standard deviation gives us more precision in the same way that a larger sample size would give us greater precision. Okay, so let's move forward a little bit, unless any of you have questions before we do so. Stop and pause.
I have a question.
Yes.
Why would the larger population size like determine a more precise? Like I just missed that last part.
I love that you asked that question,
Feel
because one, you asked it, but two, there's a subtle difference in what you said and the question I would love you to ask. So I'm going to rephrase it just a hair. You asked, why would the population size matter? And that's not something I said. It's the sample size that matters. And the larger the sample size, and one, the more precisely our estimate, y bar 1, will estimate mu 1. You spotted in that last course, more data is good, not because more data reduces the bias, but increases the precision. Would you rather have 50 rats' tail lengths to estimate the average rat tail length, or only 5? I'm thinking I'd rather have 50, because across the 50, it's going to flesh out my understanding of the whole population pretty darn well. And so because I've got more data, I can more precisely know about the population from which I've sampled. So more data, more precision. So Caroline, did that get to the issue you were raising?
Yeah, that makes a lot more sense. It's all about, the sample size, and that makes more sense. Thank you.
Yeah, and I'm glad you asked it, because there's not just one person, but there's always many people at the beginning of every term who keep thinking about the population size as mattering, because, n is referring to the number of values. Well, it's easy to think n is the number of values in the population, but no, it's the number of values in our sample that matters in nearly every single equation in a stat class. Okay, so what I want to do is go forward. Okay, so our confidence interval procedure, which tells us an estimate of the unknown truth. We're trying to estimate mu1 minus mu2, so take the difference of the sample means, plus or minus a margin of error. And the margin of error has two separate parts to it. One is the standard error that we just talked about, which, again, more data, more precision. So indeed, the standard error will go down with more data. But this other term is a number that that earlier stat class probably called your T critical value. I like to call it T sub alpha over 2 for some reason. Basically think, how confident do you want to be? And how many data points do you have? The confidence level is almost always 95%. That's what you get by default from JMP. You can adjust JMP to use a different confidence level if you want, but I never do, at least in a class case, because your faculty in your later classes invariably will be wanting you to use 95% confidence levels unless there's something particular about the problem you're looking at. And we're going to point you the right direction there too. But by and large, most everyone, most all the time, uses 95% confidence. So I'll just use that. Okay. And this number for degrees of freedom, it's something which in the earlier stat class, they probably told you how to calculate it. And I'm going to sort of walk past that real quickly and say, if you're using the software, it's going to automatically do the right thing for you. Okay, so I'm good to go with my method. You could often even think about it as our value for T is about 2. 2 standard errors up and down is usually about 95% confidence. Okay, so moving forward a little bit. That method for degrees of freedom, yeah, that earlier stat book that you have used this equation. Don't worry about it. I'm going to say, what if we have data on, and I think I opened these data earlier. Good. What if we have data on the number of births per day in New York City across the 5 boroughs, okay, during a period 9 months after the Great Blackout of 1967? So you're thinking, this is old data, but it's from the New York Times, and so we got to go with it. In 1967, the power went out near Niagara Falls, New York. And if power stations go out, you know, the one that produced the power, electricity sort of like naturally wants to flow into the empty space that had been taken up by the electricity in that part of the grid. And because it went down in Niagara Falls, all of a sudden, other power generating facilities also went offline. So basically, think Washington, D.C. to Boston to Toronto to parts of Michigan were all lacking electricity. Okay. And in New York City, there were like people stuck in elevators, and there are people who were at work and trapped and really couldn't get home so easily, except for, you know, because the trains, the subways, they weren't working. So they had to, you know, walk or take the cab. This is a drag. And the New York Times was noticing for 3 full days, everyone's lacking power. So the question came to mind, hey, what do people do during power outages if there's no work and no nothing to do? And their theory or hypothesis, I should be careful, their hypothesis is they're having more sex. And so they went to the birth records about 8, 9, and 10 months after the blackout to see if the birth rates were lower, higher, and then lower again. Now, that's not a pattern that was found. But during 25 days in August of 1968, we do have an interesting pattern that I want to show to you. And that is every day in August, like the first, it was a Monday, the number of births in all of New York City was 451. And it happened to be a weekday because it was a Monday. Okay. Across the different days of the week, you can see go, oh, Saturday, that's labeled a weekend day. Weekend day, weekday, week. So Monday through Friday are weekdays. Saturday and Sunday are called weekend days. And there was this pattern, which seems interesting to me, that on weekdays, we had 19 of them. The average number of births was like 454, plus or minus like 10. On weekends, we had an average of 377 with a margin of error plus or minus like 22 or so. How many more births do we have per day on weekdays than weekends? We've got data here that help us tackle that question. Literally, you can plug numbers into our equation for the standard error of the difference of the two means. We get out at 12.1, 7.3 degrees of freedom. I want to just show you how GMP will do that for you. If you've got data on 2 different groups, and a column telling you which group you're from, and then a number you want to compare the average of between the 2 groups, you're home free. Under Analyze, fit Y by X, and I don't want to sort of tell you why it's called fit Y by X, but we'll see that pretty soon in the next week and a half. Under Analyze fit Y by X, we're just simply asked, what depends on what? I'm thinking that the average number of births may depend on the type of day. How does the average number of births depend on the day? Or does the average number of births depend on the day, type of day? Great question. You click OK. And you get the data out in sort of a graphical form. JMP does a nice thing and sort of obscures from you some of the things you might be interested in until you ask for them. But it does present to you the data in a way that they think, well, of course, everyone wants a picture. I'll make you a picture. And with JMP, you can spot in this upper left triangle, and the lab will walk you through this a few times. In this upper left triangle, you can frankly say, I want to make this look different. I want to show like the average for each group. So for like the weekdays, there's an average, which is shown. Now the weekends, the average is shown. So you can tweak the graph. You can make it into a box plot if you'd like, no problem. Okay. But what you can do with our friend, you could show me the means and the standard deviations. No, okay, so that gives data set summaries, but you could also turn on what's called this T procedure. It's called a t-test, but we haven't emphasized the test just yet. We're doing the confidence interval, but still a T procedure. And you can spot here in the output where it says degrees of freedom. Oh, I calculated that for you. You've got the two means, you got the two standard deviations, you got the two sample sizes, you get a standard error for the difference, and then the corresponding degrees of freedom. So yeah, we get our standard error. If you do it by hand, great. If you do it with the software, also just fine. So our procedure here basically says, take the difference of the sample means, which I got here about 77, plus or minus about 2 standard errors. And when I say about 2 standard errors, it's plus or minus literally, it depends on the degrees of freedom. That previous class showed you how to do that. I'm de-emphasizing that this term in 313. Yes, you can remember how to use the t-table to find exactly the t-value of 2.365. I'm saying, you know what? All you got to do is go down to the very output where it says, you know, the upper end of your confidence interval is 105. The lower end is 49. 77 is 28.2 units of 28.6 units above the lower end, and 77 is 28.6 units below the upper end of the confidence interval. The confidence interval is 48, or I should say 49 to 106. So we've done all of the calculations you need to do. Yeah, literally here, we've looked at weekdays minus weekends, and we got a positive difference. The software said, no, put weekdays first, weekends first, weekdays second. The software will sometimes choose for you the order differently than maybe what you would prefer at first. In a later class, I'll show you how to adjust that to get it in the order that you like. But frankly, if I say that the average number of bursts on weekdays is 77 higher than on weekends, with a margin of error of 28.6. Is that about the same as saying the average number of bursts per day on weekends is 77 lower than weekdays with a margin of error of 28.6? It's the same info. Same exact information provided. Okay, so our confidence interval procedure tells us a range of plausible or likely values for how many more bursts on average you have in weekdays to weekends. So let me give you an interpretation of this range, which is approximately 50 to 105. So I'm going to round a lot. On weekdays in New York City, there's 50 to 105 more bursts per day on average. We're 95% sure of it. We are 95% sure that there are 50 to 105 more bursts per day. Now, could we be more precise? I'm sure we could. If we have more data, you would have greater precision. The standard error number would drop. That 50 plus or 77 plus or minus 28.6, we could make it narrow if we simply had more data points. Any questions on that so far?
Professor, could you re-say the interpretation of the data again?
Yeah, so this confidence interval, which is 77 plus or minus 28, I'm rounding to get 50 to 105. We are 95% sure that there are, on average, 50 to 105 more bursts per day, on average, in New York City than on weekdays. Weekdays have 50 to 105 more bursts per day than weekend days. So Brenna, right?
Yes.
Did that?
Yes,
that
makes sense.
Okay, good.
Thank you.
Any other follow-up questions? Because the interpretation itself is one of those tough things, but fortunately, we're going to be practicing this a lot over the next short period of time. How to interpret confidence interval.
I have a question.
Oh, sorry.
Oh, no, go ahead.
Well,
Oh,
yeah, Caroline first, then Nico.
Thanks. Sorry, Nico. I was just gonna ask, is there ever a like negative standard error? And like, what does that mean if it's a negative instead of a positive?
Great question, and no. So
Oh.
your equation for the standard error is right here. The standard error is it's the square root of, well, those are all positive numbers. So positive divided by positive will be positive. Another positive divided by another positive, yet again positive. So it's the sum of two numbers, I guess. Okay, so if the standard deviation was exactly 0, which is goofy, if we had 0 plus 0, the standard error would be 0, but that never happens. So standard errors are always at least 0. And if they're more likely greater than 0, it means, yes, it's plus or minus a certain amount. Yeah, so if there was an error in your calculation somewhere, I would probably look at the root as the nature of why you got a problem. Or, maybe you had a subtract instead of a plus. On my calculator, they're right next to each other, and that's an issue. So I thought a thumbs up from Caroline. Nico.
Yeah, so I'm actually not really sure if this is even like a valid concern or not, but if you look at the table that you had pulled up earlier, yeah, that one, you see that the standard error obviously for weekdays is lower because there's a higher sample, right? So if we want a lower standard error for weekends, then we have to take more weekend days, but we want to offset that by also taking more weekdays. So as a result, both the standard error for weekdays and weekends would decrease, right? But would the ratio of standard errors stay relatively the same? And is that a concern for data or not?
Okay, so let me rephrase your intro, and then I'll get to your question. The intro said, you know what, if we want a smaller standard error to have more precision in knowledge of the difference of population means, to lower that standard error, of course, if we had more weekends, because shoot, we got a 6 in the denominator somewhere. If that were larger, that would be great. So what if we wanted 12 weekends? Twice as much data. Well, you probably wouldn't ignore the weekday information that is provided. You'd probably get another 19 or 20 weekdays to go with the additional 6 weekends. So in this case, both sample sizes would naturally go up together. And if the standard deviation in each of the 2 separate samples were to increase at the same rate, unfortunately, actually, I shouldn't say unfortunately, fortunately, the standard deviation squared, even if those both remain about the same as what they were, because they're squared, when we have these N1 and N2 going up, you will have the standard error for the difference decreasing if N1 were 4 times what it previously had been, and N2 were 4 times what it previously had been. The standard error would be cut in half. But to get to your point directly, the ratio of the standard error for each individual group would not remain the same. Of course, it's probably a good mathematical question, but I'm not so concerned about that. It's an artifact of this situation that we have the 19:6 ratio of weekdays to weekends so far. And if we continue to sample, we would probably continue to get data points according to that. But the square root will change things up. So Nico, did that get to your question?
Yeah, that makes sense. Thank you.
Okay. Anyone else want to follow up on any aspect of this so far? So yeah, I've been in Zoom meetings where like someone says, okay, let's vote. And then all in favor do this, and it's like sometimes hard to hit the mute versus unmute. So I'm trying to wait patiently. But if I start on in something else, and then one of you jumps in, I definitely want to give preference to a question, even if it took a while to sort of foment, whatever the word is. If it took you a while to get the words out and or unmute, perfect. I want to give preference to you over whatever I might say, okay? So even if I look like I've moved on, definitely jump right in. Don't be that dinosaur with a small hand. Okay, my confidence interval, got it done. How about a hypothesis test? The confidence interval really is a question like, hey, how much higher is the number of bursts per day on weekdays than weekends? And that's sort of like a hospital staffing question. You know, okay, if we're going from weekend to weekday, how many more folks do we need to staff the labor and delivery rooms? Okay, great question. How many more people do you need? Well, mu1 minus mu2 will point you in the right direction. A different question, but a related question is mu1 different from mu2? Notice that this is a yes or no question. A hypothesis test tackles the same comparison of the same two population means with a different method because your natural question differs. I'm not saying how anymore, hey, how much more is mu1 than mu2? I'm saying, is mu1 different from mu2? So let's talk about the parts of a hypothesis test. And you've seen this in your prior stat class, but I'll just say, depending on the book you use, you either saw 3 parts of a hypothesis test or more likely 4 or 5. I've seen books where I've seen 6 and even 7 parts of a hypothesis test. I'm basically saying, I want to see if the problem says, do a hypothesis test. Tell me what your hypotheses are. Tell me for sure the test statistic. Tell me what's called the p-value, and we'll hit on this one in a little bit, and then tell me what you conclude based on your data. Now this level of a test, I always use a level of 0.05. Some of you are thinking, what's the level again? Probably doesn't matter a lot, but when it will, I will mention it then. And so even if someone doesn't state the level of hypothesis test, they probably mean they're using a 0.05 level test. So yeah, 1, 2, 3, 4 things. And if you're choosing a different level hypothesis test, tell me the level as well. And also why you chose the non-standard value for your level. Okay, so let's try a hypothesis testing question in the context of a different data set. I've got data on ice cream, chocolates and vanillas, and these are data from Consumer Reports. In 1993, they went out and, darn it, I have the wrong version. Okay, come on. Okay, here's the right version. Okay, so Consumer Reports went out and purchased ice creams in major market grocery stores from major brands, or that were from, if you will, like Publix Premium or Safeway Select. Those are like house brands. Okay, so if you're going into a large grocery store like a Kroger's anywhere in the US, you're going to find a lot of these like Breyers or Bluebell, that sort of a Texas thing, Newman's. And is the number of calories on average different between vanilla and chocolate? That's a great natural question. So is the number of calories different between vanilla and chocolate? Well, my null and alternative hypotheses tell me the 2 states of reality. The null hypothesis is always, nah, there is no difference. They're equal. On the other hand, the alternative is, no, they're different. And I'm willing to believe the alternative hypothesis if the data convince me that it's necessary. The null hypothesis is what I'm going to stick with until I'm convinced that it's wrong. So let's state that carefully. The null hypothesis, mu1, mu2, the same. Vanilla and chocolate, same on average. On the other hand, mu1 is not mu2. There's a difference between the two means. Null and alternative hypotheses. So equality is always part of the null. My alternative here is a not equal to, because my question, is there a difference? Okay. Is there a difference in the average number of calories between chocolate and vanilla? Okay, so I'm thinking, what sort of data would convince you to believe the alternative? I'm thinking if the sample means we're not even close at all. If the sample means we're quite close, you're thinking, yeah, it could have happened. You're just sampling from the two separate groups. It could easily be the case that the one group would have a sample mean that's higher than the other just due to luck. But if the sample means were quite different, you'd say, there's no way that that could have happened just by luck alone. You would want to stick with the null hypothesis of equality. It's like the scientific method. Stick with the old belief until the new hypothesis is sort of verified by the data. So let's try that again. Analyze bit y by x. Now I'm using my data on, well, does the number of calories, does it differ between the flavor categories? And these data look a lot more even between the two groups. And so I'm thinking, probably I'm not yet convinced, but I'm open to believing things, okay? So let's go ahead and I'm gonna go ahead and do the t-test. The t-test procedure starts with the null hypothesis of equality. These data here for chocolate look a lot like the vanilla. I might want to stick with the null hypothesis, but formally you do have to do fleshing out your calculation of the test statistic. And I like to take 2 more minutes. I'm sorry I logged in a little bit late. If any of you have to leave right now, I understand. I apologize, but it's on video soon. Okay, so we're comparing what the two groups are like to what they should be like if the null hypothesis of equality is true. If the two population means are the same, the two sample means should be the same, typically. So we're going to compare the two sample means difference to what it should be if the null were true. Divide through by the standard error. That's our t ratio or t statistic. In JMP, your t ratio here for free, 0.666 negative. We could plug our numbers in and get our t statistic. Again, JMP chose vanilla minus chocolate. I went with chocolate minus vanilla. The difference between JMP's choice and my choice is just the negative sign. What about our decision? That p-value at the end is technically, darn it, I don't have the p-value written down here in the notes, so let me just say it real quick. The p-value is the chance of seeing data like what we did see, or even more extreme, if the null hypothesis were indeed true. Let me say that again. The p-value is the chance of seeing like what we did see, if the null were true. So let's rephrase that here. What's the chance that vanilla and chocolate, on average, would be different by about 9 calories across our samples of 18 chocolates and 17 vanillas, if in fact the two population means were identical? That chance is like 50%. I would say you could have easily seen data like what we did actually see here. If in fact vanilla and chocolate are really equal, the chance of us seeing a 9-point gap is pretty high. I would not be convinced by these data to believe the alternative hypothesis. If a p-value is tiny, like 1 in 10,000, you might want to believe the alternative hypothesis. So let's go back to our earlier example, the ice cream folks, and Diana first.
I'm sorry, how was the p-value calculated? Was there an equation for that?
Great question. I'm glad you asked. Actually, yes, but it involves calculus and integration. And so the software just said, here you go. In that previous stat class, you probably learned how to use a t-table to get a p-value, or you did a simulation to get an approximate p-value. What I'm doing here is not exactly either of those, but It's just let the software get it for you, which is about what I would expect you would do on a test. So in other words, you're going to be given a p-value, and from that you could hit your conclusion.
Okay. Thank
And
you.
look, and looking at our last thing, looking at our earlier example with weekdays and weekends, could we have seen a difference of 77 births per day just by luck alone if really weekdays and weekends were the same on average? This p-value is like 3 in 10,000. So in other words, if every student at Cal Poly sampled 19 weekdays and 6 weekend days from 2 populations that had the same exact population mean, but the data looking like the New York City birth data, only about 6 out of all of Cal Poly students would have a difference as big as 77. It's a whole lot easier to believe that this is reflecting a real difference in the population means than it is to believe that it was just luck alone. So the hypothesis test really gives you the choice of, is this luck alone, or was it something real that we're seeing? Tiny p-value, that's a real trend. It's large p-value above 0.05. Think, yeah, I'm not yet convinced. Diana, you want to follow up?
Yeah, in that case, why do we have to calculate the test statistic?
You have a great question, and some people would argue you shouldn't have to. I would say, though, because in research reports that you read in journals here and there, they invariably do report a t statistic and the p-value along with the null and alternative hypotheses. Usually they report the means and the standard deviations and your everything. Because other people do it, they sort of expect that you'll know how to read their research results. But yeah, you're right. If someone reported to you just the p-value, you should be fine to hit a conclusion, even without the test statistic itself.
Okay, and what is the definition of the test statistic, just like in English terms?
A test statistic in general, and we'll see this in the next section and in the one after that and the one after that. A test statistic tells us a measure of how close our data were to what they should have looked like, ideally, if the null hypothesis were indeed true. But between a t-test like what we're doing here and an ANOVA, which calls the statistic an F statistic, it's sort of like using different rulers. Some people use the centimeters, other people use inches. Just get in the habit of use the right ruler for the right situation. If you're comparing 2 means, it's a t-test, a t-ratio, and a p-value based on that test statistic t. A lot of good questions.
Thank you.
So what I want to do is to say, you know what? I'm going to call it a quits today because we can't have too much stuff for too long, because otherwise, that'd be a drag. I'm going to stop the share and also stop the recording as soon as I explain what's going to happen next. Actually, I'll just stop the recording right now. What the heck?